All right, so get this. Imagine a computer that operates not on ones and zeros, but on the bizarre rules of quantum mechanics.
Right.
It's a pretty wild stuff.
Absolutely wild.
That's the world we're stepping into today, the world of superconducting qubits.
Yeah.
We're diving deep today into an essay by Jurgo Schneeppert all about how these mind-bending qubits could, revolutionize computing as we know it.
Yeah, it really is mind-blowing. The essay really highlights how we're on the verge of, this whole new era of computing.
Yeah.
We're not just talking about, faster processing speeds here either.
Right.
We're talking about entirely new ways of solving problems that are simply impossible for our current computers to handle.
So let's break it down.
Okay.
Schneeppert starts by talking about this shift from bits to qubits.
Right.
What exactly makes a qubit different from the bits in our laptops and phones?
Okay, so think of it this way.
Okay.
A bit is like a light switch.
Okay.
It's either on or off, 1 or 0.
Yeah.
A qubit, on the other hand, is like a dimmer switch.
Oh,
It can be on, off, or anywhere in between.
Interesting.
This in-between state is called superposition.
Right.
And it's one of the key things that makes quantum computing so powerful.
Okay, so superposition.
Yeah.
So it's like the qubit is exploring
Exactly.
multiple possibilities at the same time.
Precisely. And because it can explore all these possibilities, simultaneously, it can tackle problems in a fundamentally different way.
Yeah.
For example, imagine trying to find the best route out of a maze.
Okay.
A classical computer would have to try each path one at a time,
Okay.
while a quantum computer could explore all possible paths simultaneously.
Interesting.
That's a massive speed advantage when you're dealing with complex problems.
Right. So I'm starting to see why people are so excited about this.
Yeah.
But how do superconducting qubits fit into all of this?
Well, to build a quantum computer, you need qubits that are stable and controllable.
Right.
And that's where superconductivity comes in. Schneeppert explains that at extremely low temperatures, certain materials become superconductors.
Okay.
Meaning they can conduct electricity with zero resistance.
Right.
This makes them ideal for building qubits.
Okay.
Because it minimizes energy loss and helps to maintain their delicate quantum state.
Zero resistance. That sounds like a physicist's dream.
Yeah.
But wouldn't keeping these things at ultra-low temperatures be incredibly difficult and expensive?
That's definitely one of the challenges. And Schneeppert doesn't shy away from that in his essay.
Right.
But there are some really clever engineering solutions being developed.
Okay.
And the potential benefits are so huge that researchers are willing to tackle these hurdles head on.
Right.
Plus, superconductors have another trick up their sleeve.
Okay.
They expel magnetic fields.
Interesting.
It's called the Meissner-Oxenfeld effect.
Wow.
And it basically creates a protective shield around the qubit, protecting it from interference.
So it's like a force field for quantum information.
It is.
That's pretty cool.
But here's where it gets even more interesting.
Okay.
Schneeppert goes on to explain how researchers use something called Josephson junctions to actually build and control these superconducting qubits.
Josephson junctions, those sound a bit intimidating.
Yeah.
Can you break those down for us?
Think of them as tiny sandwiches.
Okay.
With 2 slices of superconductor as the bread and a thin layer of insulator as the filling.
Interesting.
By controlling the current and voltage across this sandwich.
Okay.
Researchers can manipulate the energy levels within the qubit.
So it's like a tiny quantum switchboard?
Yeah.
But how do you actually talk to these qubits and get them to do what you want?
It's all about using microwaves.
Okay.
Think of it like sending coded signals.
Yeah.
Schneeppert explains how scientists use carefully crafted pulses of microwaves to manipulate the qubit's state, putting it into superposition and tangling it with other qubits.
Wait, entanglement.
Yeah.
We haven't even touched on that yet. Schneeppert describes it as this spooky connection between qubits where they become linked.
Right.
And measuring one instantly affects the other, even if they're miles apart.
Yeah.
It's mind-blowing.
Absolutely. And that's another area where superconducting qubits have an edge.
Okay.
They can be coupled together strongly, which is essential for fast and accurate multi-qubit operations.
Okay.
That's where the real magic of quantum computing happens.
Right.
When you have multiple qubits working together entangled, exploring vast computational spaces that are simply inaccessible to classical computers.
That's amazing.
It really is a whole new world of possibilities.
Yeah, it is. And Schneeppert goes on to discuss how this quantum dance could revolutionize all sorts of fields.
Right.
Okay, let's talk applications. I'm ready to hear about some real-world problems that these superconducting quantum computers could tackle.
Okay. One area where Schneepat sees huge potential is in material science. Imagine being able to design new materials from the ground up, atom by atom, with properties that are perfectly tailored for specific applications.
Oh, wow. So we're talking about custom designed materials.
Exactly.
Like super strong alloys for spacecraft?
Yeah.
Or incredibly efficient solar cells to power our cities?
Exactly. Quantum computers could help us understand and manipulate matter.
Wow.
At a level of detail that's simply impossible today.
Yeah.
It's like having a molecular toolkit that allows us to build materials with unprecedented precision.
That's incredible. And what about medicine?
Right.
Could superconducting qubits help us develop life-saving drugs or personalized therapies?
Absolutely. One of the biggest challenges in drug discovery is simulating how molecules interact with each other.
Right.
Classical computers struggle with this because the complexity grows exponentially with the number of atoms involved.
Right.
But quantum computers could handle these simulations with ease, allowing researchers to design drugs that are more effective and have fewer side effects.
So it's like having a virtual laboratory where we can test out countless drug candidates before even synthesizing them in the real world.
That's the idea, and it's not just about finding new drugs.
Right.
Quantum computers could also help us understand complex biological processes at a fundamental level.
Right.
Paving the way for personalized medicine tailored to an individual's genetic makeup.
Wow. Okay, we've got material science, we've got medicine.
Right.
What other fields could be transformed by this technology?
Well, Schneepat also talks about the potential impact on optimization problems.
Okay.
These are problems where you need to find the best possible solution among a vast number of possibilities.
Right.
Think about things like logistics, traffic flow, financial modeling.
Yeah.
All of these involve finding the most efficient way to do something.
And classical computers often hit a wall with these kinds of problems, right? They can only explore so many options before they get overwhelmed.
Exactly. But a quantum computer, with its ability to explore multiple paths simultaneously, could potentially find optimal solutions in a fraction of the time.
Wow.
This could have huge implications for everything from supply chain management to urban planning.
It's like having a super-powered brain that can see all the possible outcomes and choose the best one.
Yeah.
This is all starting to sound pretty sci-fi.
Right.
But Schneepat makes a good point about the need for realistic expectations.
He does. It's important to remember that building large-scale, fault-tolerant quantum computers is still a huge engineering challenge.
Right.
We're talking about controlling and manipulating millions of qubits, keeping them stable for long enough to perform complex calculations and developing error correction techniques to ensure the accuracy of the results.
So there's still a lot of work to be done before we're all walking around with quantum computers in our pockets.
Definitely. But Schneepat is optimistic about the progress being made.
Yeah.
He points to several exciting developments, including new superconducting materials with higher operating temperatures.
Okay.
Which would make the cooling problem less daunting.
Right.
And advancements in qubit design and control, which are leading to longer coherence times and lower error rates.
So it's not a matter of if we'll have these powerful quantum computers, but when.
That seems to be the consensus in the field.
Interesting.
And that's why it's so important to start thinking about the implications now.
Okay.
Both the positive and the potential challenges.
Speaking of challenges, Schneepat does mention a few potential downsides of this technology.
Right.
One that caught my attention is the impact on cybersecurity.
Yeah.
If quantum computers can crack our current encryption methods,
right,
that could have huge ramifications for everything from online banking to national security.
It's a valid concern, and Schneepat acknowledges that we need to start developing quantum-resistant encryption methods.
Yeah.
Now, to prepare for the day when these powerful machines become a reality,
it's like we're in an arms race with ourselves, trying to stay one step ahead of the technology we're creating.
In a way, yes. But it's a race we need to win if we want to ensure that these powerful tools are used for good and not for harm.
This has been an incredible deep dive into the world of superconducting qubits.
Yeah.
And it's clear from Schneepat's work that this technology has the potential to reshape our world in profound ways.
It really does, and I think Schneepat's essay provides a balanced and insightful look at both the opportunities and the challenges that lie ahead.
So as we wrap up our exploration of Yurgo Schneepat's fascinating work, let's leave our listeners with a final thought.
Okay.
If quantum computers reach their full potential, what kind of world will we create with them?
It's a question worth pondering.
Yeah.
Will we use this power to solve humanity's grand challenges?
Yeah.
To push the boundaries of scientific discovery, or to create a more equitable and sustainable future?
Right.
The choices are ours to make.
Yeah, it really is a remarkable time to be alive. Schneppat's essay has definitely given me a lot to think about.
Me too. It's fascinating to see how these fundamental concepts of quantum mechanics, which have been around for like a century, are now being translated into real-world technologies that could have such a profound impact on our lives.
It's like we're witnessing the birth of a new technological era, one where the rules of the game are completely different.
And the possibilities are endless. One thing that Schneppat touches on that I found particularly intriguing is the idea of using quantum computers to simulate quantum systems themselves.
So instead of just using them to design new materials or drugs, we could use them to understand the fundamental laws of nature at a much deeper level.
Exactly. Think about it. Our current computers are based on classical physics. Which is a good approximation of how the world works at a macroscopic level. But at the atomic and subatomic levels, the rules of quantum mechanics take over. And to truly understand these rules, we need tools that operate according to those same principles.
So it's like we've been trying to understand the universe with one hand tied behind our backs. And now we're finally getting the tools we need to unlock its deepest secret.
That's a great analogy, and who knows what we might discover. Perhaps we'll finally be able to understand the mysteries of dark matter and dark energy. Or unlock the secrets of consciousness itself. The possibilities are mind-boggling.
Yeah, it's both exhilarating and a little bit daunting, isn't it?
It is.
We're on the cusp of a scientific revolution, and there's no telling where it will lead us.
That's the beauty of scientific exploration. It's a journey into the unknown filled with surprises and unexpected discoveries. And as Schneppat reminds us, it's a journey that requires collaboration, creativity, and a willingness to challenge our assumptions about what's possible.
Well said. So to all our listeners out there, I encourage you to keep exploring, to keep asking questions, and to keep imagining the future. The world of superconducting qubits is just one example of the incredible advancements happening in science and technology right now.
Absolutely.
And who knows what other breakthroughs are just around the corner.
I think Jorgo Schneppat would agree with that sentiment. His essay is a testament to the power of human ingenuity and the endless possibilities that lie ahead. And we here at The Deep Dive are thrilled to be a part of this journey of discovery with you.
So until next time, keep those minds curious and those imaginations firing.